Hi, welcome to the F5 DNS Design and Architecture video. Throughout this video, we'll be going over the DNS operations as a understanding of DNS and the inner workings of DNS, and then we'll jump into the two first exam objectives from section 1 of the F5 DNS exam blueprint. Okay, let's start by taking a look at how DNS works. DNS stands for Domain Name System, and you can think of DNS working right to left to resolve what's called a FQDN, or fully qualified domain name. Alright, so let's take a look at a client. Types in f5.com in its browser. The first thing it's going to do is check its local DNS cache. This is a cache record it could find from an earlier query. If it doesn't have the cache information for f5.com, or the record, it's going to send a recursive query or lookup for f5.com to its local DNS server, or what's called a recursive resolver. And you might notice the trailing dot at the end of the URL. This is what makes up the absolute domain name. Well, the resolvers actually process the domain name without a dot as unqualified, and they automatically append the system's default name in the final dot if it needs to. So you can think of a recursive lookup as an efficient employee-boss relationship. So the boss tells or asks the employee, I need to know information about this, and the employee will respond with everything it needs to know about that request in the background. Alright, so then the local DNS server will send what's called an iterative query, and an iterative query has the option for that DNS server to refer the client asking for the request to another DNS server, but also supplying the information that it does have. Right? So the recursive resolver is going to do all the work in the background, right? So the recursive DNS server or local DNS server sends the record for f5.com to the root servers. Remember, we're starting from right to left, so we're going to be looking at that trailing dot. The root servers are really 13 root name servers, A through M, and they're operated by 12 independent organizations. You can go to root.servers.org to see how they're all spread out. So it sends it to the local DNS server, sends that to the .root servers, asking for the next part to resolve the domain name. So that root server is going to send information about how do you reach the .com servers. Well, they're hosted by VeriSign, and it's going to respond with the name server records for the .com servers. So the local DNS server will then do that same query for f5.com to the top level domains, and these are the .com space is hosted by VeriSign. There's many top level domains like .net, .edu. They're all hosted by different organizations. So for the .com, it's going to send a name server record. How do you get to f5.com? Who has the authoritative name server zone for f5.com? Well, it's going to respond with an NS record for f5.com, and this is how you reach it. This is who you need to talk to. So the local DNS server will send the same query again for f5.com to the authoritative name server, and this could be the big IP DNS box, which we'll talk about. So this actually carries the zone and is authoritative for responding to f5.com or responding for f5.com queries. So it will respond with the IP address for f5.com back to the local DNS server. Now the local DNS server can finally cache the IP address with the A record information, and then send that response back to the client for that IP. So the client will put it back in its DNS cache and use it for next time, and then be on its merry way to reach that server out on the internet. Okay, let's take a look at some DNS terminology. So domain names, here's an example. f5.com is a domain name, and it's a URL that's owned by F5 or authoritative for that domain name. A subdomain in this example is support. And it's anything to the left of the domain name followed by a dot. The domain namespace is really a tree-like structure for responding to names over the internet. So again, it starts at the top at the root level, goes to the top level domains .com, .edu, or .net, or .org, etc. Then it goes to the second level domains. In our example, this was f5.com or google.com, etc. And if it needs to go even further, then it'll send queries for the subdomains like mail.gmail.com or support.f5.com. Alright, so a DNS lookup is simply a query to a DNS server for a particular domain, and that DNS server will reply back with IP address or information about that domain back to the client asking. A name server stores information about the zone. And there are two types of name servers, primary and secondary. If you're using both, all the zone data needs to be stored in both primary and secondary name servers. Okay, so let's take a look at some common DNS record types. So you're probably familiar with A or quadruple A records. A is the IPv4 record and quadruple records are IPv6. And these are simply used to resolve a domain name to an IP address. A canonical record or CNAME record is an alias to another domain name. It's important that you know that it can never directly tie to an IP address. It's always a domain. So for instance, we have alias.example.com. That might link to example.com. NS records or name server records are used to communicate with other DNS servers. So remember when we talked about that full chain of a query or how DNS works, it always points back information to another DNS server if it doesn't have information itself. And these are generally primary or secondary name server records. Alright, so an MX record is a mail exchange record used to direct email to servers for a domain. So if you want to find out the mail server record for like example.com, then you might receive a response back with mail.example.com. And if you have multiple mail servers in your environment, the lowest priority or lowest number is the highest priority. So if you typically 0 is used for your main server, and then it would start going down the list or up in priority if that first record is unable to deliver mail. Okay, so let's take a look at our first objective from the F5 exam blueprint. So it's 101. We're in the Design and Architect section, and it is to identify customer requirements, constraints, and challenges related to DNS. So we're going to go over the functionality and the limitations of the DNS protocol. We talked about some of the hierarchy and the roles related to the DNS protocol. And then we're going to get information about a customer's need for high availability, security, and management for DNS in their infrastructure. Okay, so the limitations of DNS. So DNS can determine whether the application or website content is available, but it doesn't really care if it's up or running. So there's no way for DNS to determine if a site is really up. In addition, DNS has no real ability to distribute load. It'll continue to use all the IP addresses even if the application supported by that IP is overloaded or down. there's no real ability to persist or keep an application stateful. Cannot guarantee it uses the same IP address. So if you go to a particular data center and build a shopping cart that's maintained in that data center, there's no guarantee that the next time you resolve the name, you'll get the same IP address of the backend server. It also requires a lot of manual intervention and can result in high impact errors to the environment. If you're editing a bind file or doing any sort of maintenance, it's likely that you'll need to restart services, or you possibly have an error in the config file that could cause a lot of downtime. And additionally, it also can handle only a limited number of queries, and it's highly susceptible to DDoS attacks. Traditional DNS workarounds might have included additional DNS servers, but this only exacerbates the problem, right? Because you have more maintenance and patching and just a lot more manual intervention required. Okay, so let's see how BIG-IP DNS can solve all those issues with the native DNS protocol. So DNS is able to direct traffic to the nearest data center, and it provides the best application experience. It allows for fast and available applications. And DNS has a plethora of load balancing methods you can use to make intelligent decisions about where to send your traffic. So you can choose to send it to the closest or the best performing data center. It continuously monitors the application availability of those servers, so you're not left sending requests to servers that aren't available, and it routes traffic based on your business logic to available applications based on your needs. Next is scalability. Instead of traditional DNS and kind of putting a band-aid on the situation with more DNS servers, DNS is able to scale to hundreds, thousands to millions of DNS queries per second based on your licensing and hardware platforms. Okay, now that we got that under our belt, let's take a look at the next objective on the exam blueprint. It's evaluate existing DNS environment for the BIG-IP DNS solutions. Why do you need the DNS BIG-IP platform in your environment, and to look at some of the solutions for it. So a certain scope and scale for DNS requirements, understand the limitations, maybe your existing DNS provider, and the change control process related to integrating the BIG-IP DNS into your environment. Okay, so the first point about Objective 102 is we'll talk about scaling DNS. So the traditional way DNS was scaled was using a load balancer with more DNS servers. When we kind of talk about the paradigm shift where the BIG-IP DNS takes out both the firewall capabilities because it is an ICSA certified firewall. So the firewalls are not a bottleneck to DNS performance. It's also able to integrate the zone information from your existing DNS server and act as a hyperscale DNS performing server. You can also utilize rapid response mode for up to 200% your response per queries. It also provides 500 times the performance of traditional bind. And the administrator can maintain their own management zone. So if you have Infoblox or BlueCat, Nominum, or other servers such as Bind or Active Directory, you can use the F5 as an authoritative DNS server, so you can do zone transfers to the BIG-IP DNS. So really use the capability that the BIG-IP DNS platform has with high response times and using DNS Express. Okay, and another way to scale DNS is really optimizing the local DNS. So we can essentially get rid of the traditional setup where we have a firewall and one DNS resolver, now we can use the Big IP DNS in place of the firewall, so the firewall is not a bottleneck, and the DNS platform can perform its DNS services much faster than a traditional firewall could respond or pass traffic through. And then we're able to increase the amount of DNS resolvers on the back end, all doing this efficiently and appropriately, maybe with different zones for a specific like an internal zone and an external zone, etc., and do zone transfers to the Big IP DNS platform. So we're able to optimize and scale DNS at the local DNS level as well. And using the F5 DNS firewall, it's able to inspect and validate protocols while dropping invalid requests and refusing unsolicited responses. Okay, so let's look at a service provider network example diagram. So the challenges a lot of times ISPs have is as they grow to millions of subscribers, there's potential to create bottlenecks in different parts of the network. So the Big IP DNS, if you look at the boxes in blue, can really eliminate all of those bottlenecks by using these services at their respective locations. So let's take a look at the mobile core, for example. We have the DNS platform listed in here with GSLB functions, and it's able to monitor the service nodes or the packet gateways to make sure you're sending subscribers to a packet gateway that is optional. So, and then we'll swing to the core network services. We're able to provide DNS authorization, authoritative zones, and local zones, as well as caching and transparent caching. This helps with low latency. It provides the ability for low latency. And then we also have the DNS 6-to-4 translations, right? So if users are on IPv4 or need to translate to IPv6, etc. So those are just some of the cases where Big IP DNS can act as eliminate all those bottlenecks we talked about, as well as even provide advanced firewall protection at each section of the network and the corresponding layers. Okay, so let's zoom in on the mobile core network for an ISP. So you can see here that we've got a lot of subscribers, and we're able to offload the DNS resolver in the middle and protect that from getting a lot of queries. So the Big IP DNS is able to use its DNS caching and resolving functions and deliver high performance to the users by protecting the DNS resolver, so you could potentially scale further as you're receiving fewer requests. It's a low impact implementation that means the subscriber and the servers are really unchanged in behavior while you scale DNS and increase the optimization for the caching functions. Okay, so for the last part of Objective 102, it talks about change control. So we'll start by looking at TTL. So TTL is a time to live, and it's basically the expiry time of the record. So for a normal site, you can expect 86400, which is in seconds, and that's 1 day. So this means that once a DNS server or other DNS client has requested the record, it'll hold that in cache for up to a day before requesting that data. So during the migration, for a quick cutover, you can start lowering that time to live. by 3,600 seconds, which is 1 day prior, and 600 seconds, it's 1 hour and 60 seconds from 1 minute. This will help create records to request that data again as they get lower before you cut over, so that way they're still not stuck on the old site. So additionally, you can lower the new TTL records temporarily. So when you put in, let's say, the DNS platform, you can lower the TTL records. So as they're sending out information with the TTL value, that it would be a really low value, like 60 seconds. So if you needed to roll back to your other platform and send new DNS queries, that the clients over here would be able to request that data and not use what's in their existing cache functions. All right, and the second deals with replacing your existing bind DNS server or your internal DNS server. So one of the appropriate things you can do when you have the DNS box is to disable all of the interfaces and then hook up the cables to your switch, and then during cutover you would remove the existing DNS server from the network. So this would be like a bind server. You would remove that from the network. Before doing that, you would do a zone transfer to DNS, so it has the information for that zone, and you would configure DNS to use the same IP address as the bind server did. So hopefully eliminating any type of duplicate IPs, you're able to basically swing over the bind server using the same IP address and have it be a self IP. So if there's still clients out there that need to resolve to the same IP that they once had, then Big IP DNS can perform that function. Okay, so in summary, we talked about how DNS works and operates, some of the basics there, and then we jumped into the DNS terminology and some basic or common DNS record types. And then we looked at the first two objectives on the current F5 exam blueprint regarding the DNS design and architecture. So I had a lot of fun with this video again. Thanks for watching, and I'll see you in the next one.